Wait, do your Lewis and Clark here. Do your Lewis and Clark.
What do you want me to do, my Lewis first?
That way?
Yeah, which,
Okay.
I think it's lower.
There's my Lewis.
Yeah.
Here's Clark. Hello, I'm here with my colleague Brad Young, and we have been exploring the landscapes of catastrophe for well over 2 decades now. And one of the things that we've been very interested in is the great floods that have swept over North America from time to time, mostly concentrated at the end of the last ice age. One of these great floods was called the Bonneville flood, named after Lake Bonneville in Utah, which was a giant lake that existed during the latter stages of the ice age, during we would call the late Quaternary, that formed on several occasions and then disappeared. The modern Great Salt Lake is a remnant of the great Lake Bonneville. The famous Bonneville salt flats are also a relic of that lake because all of the mineral sediments that swept into the lake from the surrounding mountains settled to the bottom and formed a perfectly flat plain that is now used for testing high performance vehicles. So we'll just jump right into it here. Harold Mall, with the U.S. Geological Survey, was the geologist that did the original work demonstrating that there was a gigantic outburst flood from Lake Bonneville. And that's what we're actually going to be talking about here, is that flood that was formed from the overflow of gigantic Lake Bonneville. Malde says the enormous size of depositional and erosional features produced by the Bonneville flood imply a peak discharge of extraordinary volume. This is what he said back in 1968. When a lot of this period when there was a lot of recognition of gigantic floods. It came on the wake of the acceptance of J. Harlan Bretz's ideas about the Missoula Floods and the formation of the Channel Scablands, which pretty much became mainstream, accepted by the mainstream between the mid-60s and the early 70s. This is the northern part of the basin. You can see right here is the northern part of the Lake Bonneville Basin. And this is the remnant of Great Salt Lake. And during the maximum high stand of the lake, which occurred between about 15 and 18,000 years ago, all of these valleys in here were filled. And one of the valleys, which was the lowest point on the perimeter of the lake, was right up through this area. And when the flood spilled out, it followed this valley here out onto the Snake River Plain, which is this large feature that we see right here. And we can see the channel of the modern Snake River snaking its way across the plain there. Yellowstone hotspot is right up here. And the idea is that around 17 million years ago, that hotspot began extruding large amounts of lava, that there's a mantle plume beneath Yellowstone there. And over the course of 17 million years, the North American plate has moved over that hotspot. And as that moved over that hotspot, the upwelling thermal energy basically melted the overlying landscape and produced this large sweeping feature here. This is a study from the early 90s on the Great Basin, and you see Lake Bonneville was not the only huge lake in that basin and range area. In fact, as it says here, nearly all closed or formerly closed basins in the Great Basin have ancient strand lines marked by lacustrine bars. That word lacustrine simply means lakes, splits, spits, embankments, terraces, deltas, and wave-cut cliffs at elevations well above the playas or permanent lakes of today. The impressive shore features of Lakes Lahontan and Bonneville prompted their study by the U.S. Geological Survey more than a century ago. About 120 pluvial lakes existed within the Great Basin during Wisconsin time. I would mention that Wisconsin time is generally time from just over 100,000 years ago to about 11,000 years ago. Goes on to say, Lake Bonneville became the largest pluvial lake in the Western Hemisphere about 17 to 15,000 years ago. At its maximum, it inundated several coalescent intermontane basins, meaning in between the mountains, right, in northwest Utah, extending into Idaho and Nevada, an area of about 51,700 square kilometers, almost the area of Lake Michigan, and had a depth of about 315 meters. And at the bottom I've shown you here that 51,700 square kilometers is about 19,950 square miles. 315 meters is just over 1,000 feet, about 1,033 feet. Today, the only permanent lakes are Great Salt and Utah lakes. Lake Bonneville's history remains controversial. Nearly every serious researcher on Lake Bonneville since Gilbert has come up with a different interpretation. Here is the Basin and Range Province. You can see it's almost like a circular feature. And what you have is many mountain ranges separated by these basins. And all of these basins have these flat floors. And it was these flat floors that are remnants of these 120 lakes that occupied this great basin during the late Wisconsin times. So in the next slide, what I'm going to show you is a reconstruction if all of those basins were occupied by lakes at the same time, which I'm not necessarily saying, but if they were, you would have pretty much something like this. And they weren't all occupied at the same time. But nonetheless, there were vast bodies of water in what is now an extremely arid environment. So clearly we've had some very serious environmental changes in the last 10 to 20,000 years to get from something like this to something like...
And that image includes parts of Nevada, Southern California,
Yes.
Arizona,
Yes.
Utah, Southern Idaho. That's quite an expansive view there.
Yes, and you can identify this dark green right here is Death Valley. In Death Valley, we won't be talking about this today, but Death Valley also had a large lake occupying it that was nearly 1,000 feet deep. And as Maldy said, the Bonneville flood mostly occupied the same canyons and valleys that exist today, but it modified them by causing extensive erosion and by depositing great piles of flood debris. It left a vivid record of its cataclysmic passage. And that's what we will be looking at, some of these slides, so you can get an idea of what the erosion and deposition features are that first clued Harold Malday into the realization that there had been this extraordinary flood. So here are just a few statistics. Lake Bonneville at its maximum had an area of about 20,000 square miles, a maximum depth of 1,033 feet. I have not been able to find a good estimate for the volume of the lake yet. So at some point, hopefully I will find that. We will add that into our data there. The highest elevation of the Bonneville shoreline was 5,090 feet above sea level. And the elevation of what is called the Provo shoreline was 4,765, just somewhat less, about just 325 feet less. Okay, so, excuse me, the highest volume of the lake reached up to a sill, if you want to call it a sill, there in southern Idaho, in the what is now called Red Rock Pass, which we will see a slide of in a second. The elevation of that sill stabilized the lake at that level for some indeterminate time, but the sill was composed of highly porous tufaceous rock, tufa, which is a volcanic rock, and that was laid up over hard limestone bedrock. So the idea now is that the Great Bonneville flood was caused because the water overtopped this softer rock and eventually flowed over it in the form of a river, ate it down to some level, some threshold level where the pressure of the great body of water behind it was too great, and it was able to sweep the softer rock out. And over a period of a couple of months, the lake level dropped by 320, 330 feet as all of this water poured out over Red Rock Pass. The water level dropped, and then the lake restabilized at that hard limestone sill, and that is the Provo shoreline right here. You can see that right now the modern elevation of Red Rock Pass is right about 4770 feet above sea level, only 5 feet difference. So that's a meaningless difference. There have of course been isostatic adjustments that would throw that off, but so there was a shoreline then that formed at the elevation of Red Rock Pass. The Bonneville flood itself had a peak discharge of up to 41 million cubic feet per second, which is an extraordinary volume of water. It's an order of magnitude less than the Missoula floods, but it's 2 orders of magnitude greater than any modern floods that are of record. Total volume of water discharge was 1,140 cubic miles, give or take, or 4,670 cubic kilometers of water. That is a lot of water. So here is an aerial view from about 25,000 feet up, where you can very clearly see the remnants of shorelines along the mountain slopes here. So here to this side, which would be to the west, is where Lake Bonneville existed. And I did a very crude graphic just so you can kind of see where the body of water generally occupied and left these shorelines behind. And on this view, you can very clearly see shorelines on the opposite mountains. And those shorelines are roughly 1,000 feet, actually 900 and some feet above the valley floor here. And this is the northern section of Salt Lake City right here. This is probably not Salt Lake City, but part of the urban area of Salt Lake City. And in this view, you can very clearly see the high water mark coming across the mountain faces right in here. And that is strong testimony to the former existence of a lake. As it says here, this is the view looking east towards the Wasatch Mountains, north of Salt Lake City. The water erosion from Lake Bonneville is clearly visible on the flanks of the mountains. And here are the 2 key shorelines, the Bonneville shoreline and the Provo shoreline just north of Salt Lake City. I'll put a little simple graphic in here. I'll do a magenta line so you can see the uppermost shoreline, and then I'll do a green to see the lower shoreline.
After it dropped 300 feet.
Yeah.
And these are features that are very visible on the sides of the Wasatch Mountains, and 1 million people live around there,
Yeah.
and some small percentage really recognize what that's telling them.
Some small percentage, right. Yeah.
So you're really introducing the language of the landscape here that people can learn to read.
Right. And part of, I think, what we're trying to accomplish here is to show people that these features are very ubiquitous. They're all over the place. And there's pretty much nowhere that you cannot find some imprint of some great catastrophic event. And we'll be covering other areas, other geographic regions in upcoming videos, so people can realize that, yeah, a lot of this stuff is right. You don't have to travel all over the world to see some of this stuff. It's right in our backyards.
Exactly.
This is the Sawtooth Mountains, and what we have here are called cirques. These are these bowl-shaped depressions that were the accumulating grounds for mountain glaciers. And so this is evidence right here that there was once extensive glaciation in these mountains, evidently going back to the last ice age. The melting glaciers on these Sawtooth Mountains would have drained into the Payette River watershed, which flows to the Snake River via the Boise River. And so I'm asking the question, could the melting of these glaciers contributed to the Bonneville flood? And I think the answer would be that these glaciers melting contributed to the rise of Lake Bonneville.
Sure.
Which obviously was necessary before it could overtop Red Rock Pass. And this is a photograph taken within Red Rock Pass itself. And this is a butte within the pass where you maybe can see on here there's a reddish colored rock, and that's where it gets its name from. The red rocks, which gave their name to the overflow spillway of Lake Bonneville. At this point, the waters of the, I've got in quotes, Bonneville River flowed 300 feet deep. The rock outcrop, and that's actually a very conservative. In some places, in some of the constrictions, it deepened up to 400 feet. The rock outcrop here is an eroded remnant of the former landscape. The elevation of the high point on Red Rock Butte is about 5,050 feet, which is just below the original elevation of the pass. The highway is about 4,770. Actually, this is the edge of the highway. This is a railroad track here, but this whole area below here is about 4,770 feet above sea level. This is virtually the same elevation as the Provo shoreline of Lake Bonneville. So basically what we're saying is that not too far above Red Rock Butte here was the pre-flood landscape surface up here. Got that? Once the water flowed over, it rapidly ate its way down to this level, and then it stabilized. And this is a remnant within the pass of the former rock, which would have been continuous all the way across the pass, maybe with some exceptions. There may have been, and probably was, some canyons or channels already through there that were occupied by the floodwaters.
But it's a very flat valley floor there, so there's sediments that have been pushed through there
Yes.
as the water channelized to escape.
Exactly. And here is a digital map. Right here is, this is the Red Rock Pass right here. And this is what we were just looking at. That Red Rock Butte is right in here. And you can kind of see from this that what we have here is a converging channel that's narrowing into this constriction, and it widens into this basin. One of the things you want to understand about water flow is that when you have, let's say that, like we talked about earlier, there was a period of several months over which this lake level was dropping.
Sure.
So during that several months, you could consider that this is more or less uniform flow through here. In other words, if you take a cross section here and a cross section up here, and you measured the amount of water, cubic feet per second, flowing past any given point, it would be virtually the same, right?
Okay.
Also through here. So in other words, there's as much water flowing through this wide part of the channel as there is flowing through this narrow constriction on a per second basis. Well, what that means then is that as the water is coming into that constriction, the pressure behind it builds up, right? And it forces the water to move at a higher velocity.
Right.
Because when you have a larger cross section, the same amount of water per second can flow than if it's narrow. But if it's narrow, it needs to speed up. The velocity needs to increase in order to maintain that uniform flow. Well, what happens when water speeds up is it becomes more erosive. It begins to pick up material, the word is entrain material, picks up that material, transports that material. Once it gets through the constriction and it opens up again, the water now slows down. When it slows down, it loses its competency to carry materials, and then it begins to deposit those materials. And generally, what it'll do is it'll deposit the heaviest materials first, and then as you get down current, it'll be successively finer degrees of material. So oftentimes when you look at a flood deposited outcrop, oftentimes some of these are called valley trains, where you may have a protuberance, let's say a hill projecting into the flood flow. So the water behind that projection tends to slow down, right? So it will build a bar behind the projection, and it's called a valley train. And you can look at that valley train and you will get what is called a paleo current indicator, which is by looking at the size of the sediment, it'll diminish down current. So by looking at that outcrop, you can tell which way the water was flowing.
Identify the flow, correct.
Yeah.
So also there is a pull-off, right? There's a geological marker at that site, so people that are in this neighborhood are
Yes.
passing through
Yes.
north of Salt Lake to Pocatello or American Falls there in the Idaho.
Yeah, this
Plane.
photograph is probably taken from the pull-off. This is a photograph you'll see quite frequently. So yes,
Right.
there is a pull-off
So,
there.
yeah, I think there's a path you can go over toward the
Yeah. Yeah, I think,
outcrop there.
let's see here, yeah. So then, this is just going further into the pass where it's now begins descending down towards the Snake River Plain. And this is looking north into the pass. And this is
Are
looking...
those strand lines on that hillside there? Or is just the angle I'm seeing it?
Yeah, yes, I think I wouldn't be surprised if those were. I mean, they're pretty faint, but it does appear that those could be strand
From
lines.
this angle, they look fairly parallel and even.
Yeah, and strand lines are basically horizontal lines that are left behind after the draining of a body of water. We've seen many of those and have documented many of those throughout the pathway of the Missoula flood.
Hi, Bradley Young here, producer of the Cosmographia podcast, co-hosting with Randall Carlson. What we put together here was an early attempt at a podcast, 2017, when we tried out multiple studio settings, TV backgrounds, slide screens, etc. But one we did here directly related to the Bonneville flood. I am off screen in this video, and that was due to operator error where we had no actual video of the wide shot that had both of us included and the TV. So we got Randall and the important stuff on the screen. So that's what we got for this time. Got a lot in the archives. Hope to keep bringing them out, and also have some Cosmographies coming up with Randall Carlson. Enjoy all the different offerings that are out now, and thanks for checking this one, and we'll see you soon. Hopefully we'll see you in person out in the field chasing megafloods.
So this is looking west over Red Rock Pass from the mountain range to the east. Do you remember the name of that mountain range?
I remember it being a hairy, scary, narrow road with the big drop off right next to it.
Yes, it was.
Getting across there.
It was in fact a large, a narrow, scary road up into the mountains to get this shot. But we're looking across here. The water flow is from left to right. This is from south to north. Through here, I guess the maximum discharge might have been, earlier the estimates of the peak discharge for the Bonneville flood were about 30 to 32 million, but I've seen revisions that have placed it as high as 41 million cubic feet per second. I've just kind of taken the middle here, 35 million cubic feet per second. Here's the great Bonneville River, as I'm calling it, would have been about 300 feet deep and 3 miles wide, flowing through here. So that was
Impressive.
very impressive event that had an impressive short-lived catastrophic event. And as we go north, following the path of the floodwaters, this is interstate that comes up through here. It comes up through this called Marsh Valley right here, and then makes a sharp bend to the west, and then another bend to the northwest, and then it discharges up here. This is the beginning of the Snake River Plain up here. This is the town of Pocatello. So Pocatello is right in the mouth of this, what's called now Portneuf Valley, which is this section of the valley, and the water spilled out and spread out there, and then flowed out onto the Snake River Plain. American Falls Reservoir occupies a trough or a basin that was scoured by the floodwaters as they passed out into the Snake River Plain. There's a dam down here at the southwestern edge of the American Falls Reservoir.
So that feature's always easy to pick out, even with all the labels, to see that
Yes.
zigzag right angle
Right.
coming across there right into the
That dog
Pocatello
leg,
and
exactly.
the
Yeah, it's
reservoir.
easy to pick up. And of course, this is a very impressive drive that you can make up through here. And you can make some diversions off if you want to explore some of the surrounding country. But the main highway follows the path of the flood, out the Bonneville flood, out of the basin of Lake Bonneville and through the passes and valleys and up to the Snake River Plain. And here's an aerial view
Nice.
of the Portneuf Pass. Right here, you can see this is that sharp right angle turn, and the water came through here, sloshed around this turn, sloshed around that turn, and then down here would be the Snake River Plain, and then it's spread out.
So is Pocatello built on a delta?
Yeah, I would definitely think that you would find here is Pocatello from the air. And yes, I would, it would be almost certain that there would be lots of flood deposits here, almost like you said, a delta where this water spreads out, creates this fan-shaped deposit, and the city of Pocatello is now built upon that. All right, so here's the Snake River Plain, and what we were just looking at, if you can see this, yeah, here comes 15, Interstate 15 comes up. Dog legs over, you can see that dog leg right there. There's American Falls Reservoir. So all of this water flowed out, spread out over the plain, but then it began to focus into what is now the channel occupied by the Snake River, which snakes its way across here and then heads up this way and through Hell's Canyon. And then it discharges from the north end of Hell's Canyon by Lewiston, Idaho, and
The clear water comes in right there.
It merges with the Clearwater, and then together those flow to the west and merge with the Columbia River. So we're going to look at this area right in here, because once the water becomes channelized, it becomes erosive. And we can see here what is called Massacre Rocks, and this huge deposit of large boulders here. And for scale, you can see a human figure out here. The water flowed from right to left. This is a distributary channel. So this was undoubtedly cut before the canyon floor was cut down to this level. You would have had the water sheeting in a sheet flood over the surface of the Snake River Plain. It would have then concentrated in maybe a pre-existing swale or a pre-existing channel. Once it does that, then it becomes erosive, but it'll also create distributary patterns like this, and that's what this is called. This is a distributary. So this is where water was flowing over. It then branched out to create a separate flow, but then as the flood ate this floor down of the main valley, the main trunk valley, at some point the water level dropped below this saddle here, and it then became isolated and dry. It became a fossil feature, which
It was very clear in a Google Earth image, say, where you're looking directly overhead, and you can follow those
yes,
patterns of the flow that are outside the main channel.
yeah. In fact, you can see it in this map
There
right
you
here.
go.
Here is the distributary channel right here. And we also see cataract formation here, which is the water flowing over the surface, plucking rock. And you see actually a streamlined form right there. And we see a pointed kind of streamlined form right here. And the rocks that we saw here, forming this train of rocks, is on this bar, which is right where this arrow is pointing. So those rocks are right here. So you can see actually that the water came down and through this channel, very highly erosive, probably moving at 50 miles an hour, something like that. It was also flowing over the top here, and that's what created these cataracts that you see here. So you can see there's a channel right here that was a distributary where it flowed off. But initially, what you've got a picture is that this water is flowing over this landscape. Then the water becomes focused into the channels, and then it becomes extremely erosive and rapidly then can erode the floor of the channel down. And that's what happened right here. And that's when this distributory became isolated.
And again, this is a state park that people can go visit, and
Yes.
it's right off the interstate there, Interstate 86. And, you know, they can get an up-close view
Yes.
of what this flood's power really was right through this area of the Snake River.
A really awesome road trip, which we've done now, is to basically start in the basin of Lake Bonneville and follow the pathway of the flood.
We should do it again.
We should do it again.
Absolutely.
Of course, when you get to the southern end of Hell's Canyon, you've got to stop there and basically take a boat through the canyon because there's no highways
Yeah,
through there.
jump on the raft.
But you can pick up the highway again at the northern end of Hell's Canyon, just below Lewiston and Clarkston there.
Right.
And this is the kind of things you'll see that really is a testament to the unbelievable power of this flood. These were two boulders entrained within the flowing water. They undoubtedly weren't transported that far, or they would have quickly broken apart into smaller materials. But nonetheless, they were carried in the water and dropped right here. So you can really get a sense that you know, a river or, you know, a flood that could transport boulders of that size had to be a pretty powerful
Serious
event.
power.
Serious power, yeah. And this is looking down into the modern day Snake River Canyon. I don't think anybody really knows what the pre-flood depth of the canyon was, but it had to have been considerably shallower than the modern day. And I'm guessing that there probably was a shallow river channel flowing across the Snake River plain that ultimately became exploited by the Bonneville floodwaters.
Sure.
But this canyon right here is about 400 feet deep from the rim of the cliff down to the river surface.
And that's just below Shoshone Falls.
This one is, I don't remember if this is just below Shoshone. I think this is actually above Shoshone.
I'm pretty sure the falls is right on that side.
Okay, well then, yeah, you're probably right. So Shoshone Falls is on the Snake River, about 4 miles northeast of the city of Twin Falls, near the midpoint of a chaotically eroded 14-mile section of the Snake River Canyon. Shoshone Falls was an important landmark in the geological exploration of the West, but evidence that the falls are a relic of a great Pleistocene flood has been recognized only recently. As now understood, Shoshone Falls and its associated erosional features were formed at a time of catastrophic outflow from Lake Bonneville about 15,000 years ago. And again, that's Malday writing again after his seminal paper of 1968. This is 1987, 19 years later. And this is a photograph of Shoshone Falls. What happens is as the waters of the flood come through, they will pluck rocks, and as the water flows over the rim, it'll continue to pluck rocks and erode material, and so what it does is it erodes, creates a cataract, and then as the water flows over, it eats the cataract upstream, and will continue to do so until the force of the water declines to the level which can no longer quarry the rocks, or the flood ceases altogether. So that's what we have here. We have the relic or the remnant of a cataract feature, which is usually a horseshoe shape,
Okay.
which has to do with the hydrological characteristics of water flow, which we can talk about in another video. So as it says here, Shoshone Falls is at the junction of two channels of the Bonneville flood, one along the narrow Snake River Canyon and the other on the upland a few miles north. Where the channels joined, flood erosion produced a chaotically eroded landscape of cataracts, spillway alcoves, and scablands, and the original canyon was greatly enlarged. Now this is Malday's 1987 paper, where he's assuming that the scale of the canyon was dramatically enlarged by the flood. The main cataracts begin 2.5 miles above Shoshone Falls, where the canyon is 230 feet deep. These cataracts, called the Twin Falls, plunge 157 feet from basalt to massive outcrops of silicic volcanic rocks in the lower story of the canyon. The snake then drops another 212 feet to the threshold of Pillar Falls, 1.5 miles downstream. Pillar Falls, although only 20 feet high, is surrounded by scabland crags that reach 175 feet. And here we can see in this topographic relief map, we see Shoshone Falls is right here in this chaotic landscape that he's talking about is all through here. And we can see right here is Box Canyon Alcove. So this was where an upland or overland water flow re-entered the Snake River Canyon, leaving a cataract here. We've got another one up here, the Devil's Corral, as it's called. Shoshone Falls is right here. Down here we have Blue Lake's Alcove right here, which again is indication of another upland flow returning to the main channel, and in the process eating out this alcove or cataract feature right here.
So that does show that canyon. If we were here at Shoshone Falls, you had the falls that way, and then looking the other direction was down that canyon. So
Yeah,
that was that
right.
that photograph.
There we
down
go.
That
That
direction.
was the picture right there, just below the falls, right. We actually, I don't know if you remember, we went swimming in Dirk's Lake.
Dirk's Lake, yep.
Surprisingly cold.
Again, another park. Excellent weekend road trip.
Yes.
People get out and see this stuff.
So if you live in this area and you've seen this video, yeah, we would like to encourage you to get on out. And you may have seen some of this already, but maybe this will give you a little bit more in-depth understanding of what you're looking at. Here's a closer up, more detailed map of the falls area. Here's Shoshone Falls is right in here. And this is what they're talking about, this chaotic scabland type landscape. And you see there's a lot of these little water bodies here. They occupy scour holes that were created by the turbulence within the water as it flowed over here. You see a distributory channel right here. Almost this, at one point, was probably an island within the flood. You can really see here the Devil's Corral is formed by the upland flow coming this way. And again, there's a body of water here that would have been, as the water focuses through here, it would become very swift and very turbulent, and that rapidly can eat into the bedrock. Box Canyon over here, again, that was a re-entrant from an overland flow. Echo Lake, you can see right here. Here's a channel that was cut by a flow coming in from the south side of the present day canyon. You'll see this elongated lake right there, Echo Lake, which again is occupying an erosional trough that was created by the turbulent waters. And here's Twin Falls at low water. You can actually go online and there are some nice pictures on there of Twin Falls at high water, when basically the falls is over most of this area right here. During the peak of the Bonneville flood, of course, this whole channel here was brim full, actually more than brim full. And you can see from this picture, you can kind of begin to see the horseshoe shape here, which is so common. And that's basically just because of the fact that when you have a water flow, the water in the middle of the flow is moving faster than it is on the margins. And so the faster water flow eats and erodes the center of the channel faster than the sides, the flanks, and therefore ends up creating this horseshoe shape.
That U horse shape.
Yes. And this is the view into Snake River Canyon near Twin Falls. The canyon as it exists today is largely a product of the Bonneville cataclysm, which here filled the canyon and completely overtopped the brim. Now, in the latter stages of the flood, the water would have drained off the uplands and would have been confined to the channel itself. This is near the, is it the Perrine Bridge?
That's what I was going to say, yes.
Yeah, so there's a pull off here. There's a beautiful bridge that goes across the canyon here. And I think they don't
Steel Arch Bridge.
Don't they do bungee jumping and things off that
Right.
bridge? Yeah.
There you go.
There we go, the Perrine Bridge. So yeah, this last picture was taken near the side of the Perrine Bridge, which you see right here.
Yeah, I think that's you right there.
Yeah, that's me right there. Undoubtedly. Well, that was just before I dove from here down into the river.
Yeah, beautiful spot.
So this was taken from the air, and you can really see here a beautiful example of scale invariance. The Snake River flowing within a giant, much bigger channel. It was not cut by the modern snake. The modern snake is confined to this inner channel. Now, in a modern flood, the Snake River may rise out of this channel and spread onto the floodplain here, but it did not create this larger channel. That was created by the Bonneville flood. And here's the data. The modern Snake River annual average discharge 56,900 cubic feet per second. The highest ever recorded flow of the Snake River was 195,000 cubic feet per second. The estimated peak discharge of the Bonneville flood, again, the revision of this shows that it may have been up to 41 million cubic feet per second. But you can do the math. You'll see that the ancient flood was much, much bigger and left this large channel that now has confined the Snake River to its floor. And the modern Snake River will never rise up and overtop this larger channel, short of an extraordinary, exceptional event, such as occurred at the end of the last ice age.
Well, I am trying to do some quick math. Is that 2,000 times
About 2,000.
bigger than the highest ever
Yeah.
recorded peak flow?
Yeah, roughly.
And the Snake is not a small river.
No, it's not.
But in comparison to that channel, which it's not a mile wide there, but it's over a half mile, isn't it?
Yeah.
That was one substantial flow.
It was a very substantial flow. And then in the basalt bedrock that forms the floor of the Snake River Plain is quite porous. So a lot of groundwater moves through there. And where the flood has sliced its way through the basalt, now a lot of that groundwater emerges from the surface in the form of these springs. Some of them very impressive springs. And here's the two of us out in a giant boulder bar called the Swan Falls Boulder Bar. And this is an area where you might say the flood opened up from a constricted area to a wider basin. Mm-hmm. So when it does, the material that's being carried and swept along in the flood gets deposited. And you can see here that is a pretty impressive mass of flood deposited material right there. And it really, again, a testimony to the unbelievable power of this flood as it swept over southern Idaho.
And I believe there is a cataract not far upstream from that,
Yeah.
so this is probably a lot of the debris that was
Yes,
flushed out of that cataract.
flushed out of that cataract, right. Yeah, so this kind of gives you the scale of some of these boulders that are being swept along within the flood. And of course, since they've been deposited, virtually nothing has moved them. They're pretty
Not even
much
close.
where they were dropped. And you can see here the walls of the canyon are probably 300 feet high, something like that. So, prior to the flood, you would not have been standing here. You would have been standing up closer to this rim somewhere. Just another shot. And this is the kind of thing that you see all along the pathway of the flood. This particular Swan Falls boulder bar, if I recall, was about 3 miles long. I'm not sure of the thickness. I've never seen studies showing the thickness of it. I'm going to guess it's got to be at least several hundred feet thick. But you can picture 3 miles long of this kind of stuff. Really does demonstrate the unbelievable power of a flood like this. And you can notice the little human figure for scale right there. And you'll see this kind of stuff, just massive mounds of flood deposited debris all within the wake of the flood. These are the kinds of things that you look at to try to decipher the whole hydrologic regime. Downriver from Perrine Bridge, note the large amount of flood debris that has been washed up against the face of the cliff opposite. This is not talus in the usual sense. You'll notice that the cliffs are vertical. They have not receded in order to contribute to the formation of this. This is material that was in the rushing floodwaters that was essentially washed up against this wall in the latter stages of the flood. And you see this type of thing all throughout the Missoula flood region as well.
Definitely.
And it's not talus in the normal sense of the word. It's not a gravity deposit in the same way as talus falling off of the cliff and accumulating like that. If you could sweep this away with a giant broom, you would find that this cliff face is almost sheer vertical down. And more subtle features, but still nonetheless, attributed to the giant flows through here. And you'll just see this stuff all over as you're following the route. And now when you see it, you'll know exactly what the origin of it was. And so here is the boulder bar we were just looking at here with these massive boulders on its surface. That was this feature all the way through here. And then there's more. You see there's another bar up here in this bend. And that's normal the way you see these features. Because when water flow goes around a bend, what it's attempting to do is it's trying to, all the molecules on the outside of, all the water molecules on the outside of the flow are trying to keep up with the average speed. The molecules on the inside of the flow are trying to slow down to keep up with the average speed. So as it goes around the bend, this, just like in a horse race, if you're going around the bend, the horse on the outside is going to have to be running actually faster to keep up with the horse that's hugging the inside of the bend, right? So what happens is on the outside the water's moving faster, it becomes erosive. On the inside it's moving slower, so it becomes depositional. And that's what we see right here. You'll see this, you can see this even on small creeks, in your own backyard. You will see the outside bend is going to be steeper, and then the inside bend is going to build what's called a point bar. And in this case, the point bar is composed of these gigantic boulders.
And I just want to point out again, this is accessible. You can go road down into the canyon to visit the dam site, and there's roads back in there where we were visiting, people fishing back there, so it's accessible. People go check this stuff out. Not
too many generations ago, all of these features were not accessible like they are today, and they would have been much, much more difficult to study. So we're kind of in a privileged position now, and I would like to encourage people to actually begin to learn this language of the landscape and realize that the evidence for these catastrophic floods is all around, and other catastrophic events, And this is near Lewiston and Idaho. Lewiston is on the left, Clarkston, Washington is on the right, and here's a gigantic point bar that has a gravel pit in it, and this is a very interesting outcrop right here. We visited this multiple times because here is where the Great Bonneville flood met the Missoula flood. And the arrow points to a gravel pit that's exposing this internal architecture of this point bar that you see here. It's called Tammany Bar because just beyond this knoll right here, Tammany Creek comes and flows into the Snake River. So here we see on the topographical map, the, let's see, I think we could go, yes, so the gravel pit of interest is right here, and this is Tammany Bar, and here comes Tammany Creek. So this was, again, this was a bar that was deposited, notice, on the inside of the bend, and then as you come around, the bend goes this way, and you have another bar built down here that the town of Asotin is constructed on this bar right here. So anyways, the Bonneville floods came north from off the Snake River Plain and ultimately out of Utah, came north this way, Hell's Canyon.
Through Hell's Canyon, right.
Hell's Canyon, right down here, flowed up this way, and then up here, the Clearwater River flows in from the east, they merge, and then the Bonneville flood would have flowed off to the west, where it met up with the Columbia River in southeastern Washington. But what's interesting here is, and I know many of the people watching this are going to have seen videos and have heard of the Missoula Flood and the Channel Scablands, which was a flood generally within the conventional interpretations. It was water that originated from a lake in western Montana. We're arguing that much of the water came out of British Columbia, Canada, but regardless of that, the water came south and actually was back flooding up the Snake River. Now, if you've got, let's say, a gradient this way, water is moving like this, it's going to be moving at a velocity that's dependent upon the gradient. The steeper the gradient, the faster the velocity, right? Now, what happened with the Missoula flood is you had waters coming from the north that almost came in at right angles to the Snake River channel, which was there at that point more or less east-west. When that water hit the channel, it's coming across eastern Washington, hits that channel, some of it flowed down, but some of it, there was so much water that some of it flowed upstream, it back flooded up. Well, picture now, this water that's back flooding up is moving up gradient, it's moving upslope. So what's happening is it's slowing down, right? This whole route of over 70 miles or so, it's slowing down, right? Right there, south of Lewiston and Clarkston, is where the water, the backflood of the Missoula water, came to a stop, reversed current direction, and flowed back out. So there is an outcrop that was visible back when we first visited this, which was in, was it 98?
98.
98, and we've been back, I think, 3 times since then. As they're quarrying the gravels away, it exposes this internal architecture. But what we did, in order to get a good overview shot, is we went across the river up onto these cliffs and took a shot across where you can see Tammany Bar right here. Here comes the Tammany Creek out here. The Snake River's invisible, but it's down in the bottom of this valley right here. And here is an outcrop right here. And we're going to zoom in, we're going to see that outcrop closer because that exposes where the Bonneville very coarse deposits, because it's moving down slope, is coming up through Hell's Canyon, and then it meets the Missoula backflood sediments that's coming this way, it's coming south. So these two floods met right here. Now the question is, were they happening at the same time, or were they separated by centuries or millennia? I don't think that's been resolved yet. The arrow points to the outcrop, and here we're going to see a closer outcrop, and you can see that in this Tammany Bar there are two very distinct types of sediment. Here is the coarse, bouldery gravel deposits of the Bonneville flood, and here are fine backflood silts from the Missoula flood. And then the whole thing is capped by this 5 or 6 feet of loess, which we'll have probably just do a whole video on that at some point, which is a very interesting subject of geology.
Two very distinct deposits there.
Yes, and here you can see how distinct they are. And this is all Bonneville stuff coming down below, and you can see how much coarser it is. And what's interesting here is it appears that the very final stages of the Bonneville flood were some of the maximum discharges based upon the size of the sediment that's in here. And then you can see these are basically like muds, very fine, silty. Up here, the water is moving left to right. Down here, the water is moving right to left. And I don't know if it shows up too well in here. In the next slide, you'll be able to see the foreset bedding, which is the tilted bedding, which tilts down in the direction of current flow. Yeah, it shows up quite clearly. You can see these magnificent bedding structures within the Bonneville, which shows water, sediment-charged water coming in this way, deposit, and then shearing off the top of the previous deposit and putting down more deposits on top. And so you can see these layers in here. This is our friend, the late Mark Lamonto, who was about 6'5", maybe.
It's all acting as scale man there.
Yeah. So you can see, and right up here in the upper left corner, you can see some of the more buff-colored Missoula backflood silts. Yeah, this where you can really begin to see the foreset bedding very clearly in this. And this again is what we would call a paleo current indicator, because it tilts down in the direction of the current flow. So this current flow is going like this, and it's basically sweeping gravel charged, sediment charged currents over the top of these previous deposits and laying down layer upon layer. And one final picture showing an exposure of the Missoula flood silts, and the final slide we will look at today.
Tammany Creek.
Along Tammany
Right.
Creek. Right. And here you can see, this is in a place where you can actually see where the currents were reversing direction through here. Where the limit of the backflood was, and the water washed up, basically came to a slow stop and then reversed direction. And we see all of this, some very fine ripple laminations in here that show us this area where the Missoula flood backwash basically stopped, reversed direction, and flowed back out.
And we're actually missing our scale indicator here, so this is
Yes, this is
probably only 5 inches, 6 inches.
I think that's about, yeah, 6 or 8 inches.
I remember these being, maybe just 3 inches.
Yeah, exactly.
Amazingly fine.
Yeah, so this is
movement that's just frozen in time.
This is very fine structure here, and getting into interpreting this and reading it is a whole, discipline in itself, which would be beyond what we're talking about today. So this was to introduce you to the idea of the Bonneville flood, and to show you that the Bonneville flood and the Missoula flood actually did meet at this point. And looking back at this particular slide right here, what's interesting about that is, bear in mind that down here, the Bonneville flood is going to be a higher energy depositional environment. This is going to be a lower energy depositional environment. High energy depositional environments erode, lower depositional environments deposit, and if it's generally a very slow moving water, what it'll do, it will basically bury everything that's there previously. Right? Instead of washing it away, it just buries it. When you look at this outcrop here, you don't really see much evidence of there being a hiatus between the deposition of these layers and these layers. Had there been, let's say, 1,000 years or 2,000 years, there would have been soil formed on the top of the Bonneville sediments, and vegetation, undoubtedly trees. There should be remnants of that. Somewhere in here we should be able to detect stumps, we should be able to detect a layer of vegetation. At this point, this outcrop needs to be studied in greater detail to determine whether or not that's there. But superficially, what we see here doesn't really suggest that there was any hiatus between the deposition of these two distinct layers. The final thing I'd call attention to is this interesting layer of vertically oriented up here called loess. This was material that settled out of the atmosphere after the final flood. Now, what that seems to indicate, and again, this is probably 5 feet, 4 or 5 feet thick up here, that's a lot of material in the atmosphere that settled out. A lot of material.
Oh, yeah.
So,
Blanketing multiple states.
blanketing multiple states. So,
6 feet thick.
yes, so that's another factor that needs to be considered when trying to understand this whole series of events. But one of the things that I would like to suggest here is that the Bonneville flood was not an isolated event, but was part of a much larger continuum of catastrophic phenomena that terminated the last ice age. And I think that this is where we're going to be going in the direction of future thinking about environmental change and geological change,
Right.
is most of these things have been studied in isolation. And I think the mainstream view now is that, well, you had the Bonneville flood and you had the Missoula flood, and they weren't really connected. They would just happen to be more or less synchronous in time. In other words, within a few thousand years of each other. But in the one hand, in the case of the Missoula flood, we have a giant proglacial lake held in by an ice dam. In the case of the Bonneville flood, we have a giant lake on an intermontane basin, not held in by glaciers, but held in by a soft sedimentary rock dam. With Missoula flood, the idea is that the ice dam gave way, allowed the lake to drain. In the case of the Bonneville flood, it was this sedimentary rock dam that failed, allowing the lake to drain. And both of those floods ended up being channeled into the modern Columbia River, flowed west, and then ultimately into the Pacific Ocean near the town of Astoria, Washington. And there's now a fan there called the Astoria Fan, and off the coast there is a large submarine canyon that was produced
Right.
by the floodwaters. So I think that more studies need to be done in the correlating these two particular events and ask the question, were they two independent events, or were they somehow both regional manifestations of something larger?
Something larger.
Something
for sure.
larger, yeah.
And were all these sediments carried only by the water that left Lake Bonneville, or was there more water being added in along the Idaho plain, the
Yes.
Snake River plain, that
Well, remember,
augmented those flows?
Lost River Canyon,
Yes.
that we need to maybe include at some point, seems to suggest the possibility that there were other contributing flows into.
Right.
Yeah. And how many other smaller features like that? I mean, Lost River Canyon was only, I think, carrying at its peak 3 million cubic feet per second, if memory serves me right. Something in that range. So, but still a very significant flow, where there's now basically just arid, almost
Right.
desert-like.
Right.
Right.
Mars looking.
Exactly. So this is to introduce the viewer to the Bonneville flood and to encourage people to get out and see this for themselves. And that's about it for this particular podcast.
All right. Thanks for joining us. We'll be back with Randall and more geology and more stories of the floods of the Great Northwest and beyond. Thank you, Mark, for your fine service.
Yes,
Right.
we will never forget you, Mark.